Alrighty, let's make a start. So, stationary points. I believe you're already familiar with the gist of what's going on here, right? Where you can use the derivative for finding the stationary points on a graph. You've got your local maxima, your local minima, and even these points of inflection. Now, more specifically, it'll find the stationary points of inflection. That's where you do have gradient 0 at those spots. Technically speaking, an inflection point is just where you go from concave down to concave up, or vice versa, where you sort of wobble in the graph. And that may or may not actually be a stationary point. The key example would be something like the circular function, sine and cos. It goes between peak and trough, but when it wobbles between going from the minima to the maxima, that's not actually a gradient 0 spot, and that will not be found by doing derivative 0. Which I shared a picture of. Should have shown us that. So it's these spots here, which are points of inflection, but not necessarily stationary points of inflection. So, very bare bones basics as far as finding stationary points, because they have a gradient of 0. If you know the function, you can therefore find the derivative and set that equal to 0. Derivative is all about gradient related information, so when you set derivative 0, you're essentially finding where is gradient 0. Here's our cubic. Find the derivative as per our table of derivatives. Solve the resulting quadratic equaling 0, however you want to go about that. All right, in this case, it's pretty simple. You just bring everything over to the same side and then do your square root. That'll get you the two x coordinates for which there are gradient 0 or stationary points. If you want the full point, obviously you're then going to shove that back into the original function to then get that there. So shoving that back into the original function, we're going to get the positive and negative 16 for the y values. And sure enough, that's now going to find out where our stationary points are on the cubic. That's more or less what's going on here. Any questions so far? Feel free to hop off mute or pop it in the chat. Either's fine. That's not the only use for using derivatives to find stationary points. It can also give you additional information or allow you to use additional information in the question to solve unknowns instead. So for instance, in this case, we're trying to solve for A, and we're told the additional information that there is a stationary point at x equals 3. Because we know there's a stationary point at x equals 3, immediately the first thing we're thinking of is derivative equals 0. All right, just like we saw before. So I know that when derivative equals 0, there should be a stationary point. Or in other words, f dash of 3 should equal 0. So if I can find my f dash of x, and then go from there, what I'll find is that I get an equation with only one unknown left in it. We go from this quadratic, finding the derivative gets us to this linear, letting it equal 0 and subbing in x equals 3 leaves you with only a in the equation. Any questions about that one? The next one is now going to go to the extreme. So this is probably the most complicated question in the Cambridge textbook here for 10C, question 8. Basically, we are now trying to find the stationary points, or more specifically the x-coordinates of the stationary points, but we don't really know what degree this polynomial is going to be. It's going to be an arbitrary size. It really doesn't matter, more or less, what the question's asking. As long as it's finding stationary points, or x-coordinates of them, this function ends up being pretty much irrelevant. You're still just going to find derivative, and you're still just going to try and solve for 0. It's just a matter of how complex that might look. So let's see. First up, derivative. We have a product of two functions, right? There's brackets that are separating these two terms with nothing else in between. That doesn't really count the power. So you now have product rule when it comes to doing our derivative for this. That's going to be your u, that's going to be the v, right? U and v. From there, product rule says, of course, we do our derivatives of each of those. Again, you're going to have to kind of do it a bit generically here. Power goes down the front, reduces by 1. And this is also technically a chain rule bit in here as well. So you would then, if you wanted to write out like a really expensive solution to this, you'd probably chuck this over somewhere else, do its derivative. But because it's linear, derivative of linear is just going to be that coefficient anyway. So once you get really good at doing these, you can kind of do it in these 2 steps. In fact, on your formula sheet, you do get a generic version of this where it has linear on the inside. Let me just pull that up real quick so you can see exactly what I'm referring to. This will be in both your tech-free and tech-active. What you'll see is the first 2 rows there, this one and this one, are the same thing. The only difference is that the inside of the power is a linear, and you can see how that's basically a solved chain rule for you for that particular thing. So shouldn't be too bad to compare it directly to that, right? AX plus B, there's our AX plus B. So just plugging and playing. Derivative of this, super easy, just 1, again, the coefficient of the linear. And all we're doing from there is, again, subbing that into the product rule. You're basically cross multiplying along those diagonals. And that gets you a nice and nasty sequence here that we now have to try and equate to 0. Before I go any further, I know there's a lot of numbers and letters going on there. Is there anything that needs to be clarified up until this point? Okay, so derivative being 0. This whole equation equaling 0, pretty nasty, right? You've got a plus in between these 2 things. You might start thinking of getting the x on its own, ideally, but this is still a polynomial at the end of the day, and so we still have to now treat it as if it is a polynomial of, like, you know, your cubic or above. You can't just necessarily get the x's on their own. So the way we treat polynomials is via factorization. So we try to take the biggest common factor, largest common factor, out of both terms, thus getting it into a set of 2 bracketed terms. Because when you have 2 bracketed terms like this equaling 0, that's now null factor law. Either this one or this one equals 0. As for how we've done that, it can be a bit confronting to figure out, you know, what is the biggest common factor in these. Just pretend n is a particular value, like replace n with 3, for instance, and see what you would do in that case. Well, if n was 3, then this would be cubed, and this would be squared, so the highest you could take out would be power of 2. If n was 4, then this would be 4, this would be 3, the highest you take out is 3. What you then realize by doing a few little run-throughs is this is the biggest that you can take out of both, which is why that is now out the front. And what you would notice from, again, doing those iterations is that every time you do it, you're left with just the base as its as the remaining bit that hasn't been taken out, which is why that's going to propagate back down here with no power left, because there's power 1, right? Everything else has been taken out. The remainder of this is going to go in that set of brackets. Again, you've got a plus between this and this term. And that's probably the most complexity there. Any questions as to how we've gone from that line to this line here? That can be a bit confronting. If not, the rest of this then becomes pretty easy, because you now have, again, your null factor law. Either this term or this term equals 0. So here's a solution set for the left.
Could you explain that line again?
This one?
Yep.
Yeah, sure. So we've got 2 terms separated by a plus, and one of the factors involved shares the same base. So that's allowing us to do some factorization, basically. So you can see this has got a 2x minus 1, this has got a 2x minus 1.
Got it. Nice.
Well, that's all you need? Yeah. Cool. Yeah, so this equals 0 for our null factor law, and solving that, you know, you would just take the n minus 1 root of both sides. Doesn't really matter what this is, you just root both sides, and then finally get the x on its own, nice and easy. This one here, although there was a bit more rearranging to be done, especially with a bit of, is there a bit of grouping? Yeah, there's a bit of grouping to be done here. Expanding that bracket set out, you got an x term here, an x term there, which need to be grouped, and then finally everything else can be thrown over to the other side. In this case, all we cared about were the x coordinates, so that's where we leave this question. If it then wanted y coordinates, well, we would be in a bit of trouble because shoving that into this, the x equals a half one wouldn't be too bad, but that would start getting a bit crazy. So we can see why they've reasonably stopped that from being required, the y coordinates there. But in theory, doable. That's about it for how complex finding stationary points would get. Any final questions before we move on to a bit of practice? Wait, okay. Let's try a nice and simple, well, maybe not too simple. Let's go with 2b here. Make the derivative at least a little bit challenging. Yeah, 2b, find the stationary points. So that's what we're going to aim for. Start writing it up. In the meantime, let's have a think about how we would solve it. Finding stationary points. What is required?
Derivative.
Yep, taking the derivative. How do we take the derivative of this function?
You can use product rule.
Yep, product rule. We've got x multiplied by natural log 3x, product of two terms, product rule. U equals x, v equals natural log 3x. U dash is super chill, x just goes to 1. V dash, a little bit more challenging. How do we find derivative of natural log 3x? I'll pull up the table of derivatives as well if you want to.
Is it 3 over 3x?
Yeah, it will become 3 over 3x, which then of course simplifies down to 1 over x. So the log is a bit of a funny one where it doesn't actually matter what the coefficient is here, so long as it's ax, it ends up cancelling itself out always. Sweet. All right, we have what we need. What we're going to do is now our cross multiplication. So x over x is just 1. So we're going to have, maybe we should say dy dx because we started with y. Dy dx equals 1 plus 1 times natural log 3x, so natural log 3x. Nice. All right, we have our derivative. What are we going to do with it?
You can find the x-intercept.
Yep, find the x-intercepts of the derivative function.
Yep.
Yep, sweet. So setting the derivative equal to 0. The whole purpose behind that, of course, is because stationary points have gradient 0, derivative being a gradient function. This will now be a little test on who remembers their logarithm solutions. So how do we start solving that?
You can take 1 to the other side.
Yep, that's good. Natural log 3x equals -1.
Well, you just change the format to the exponent.
Yep.
So e to the -1 equals 3x.
That's it. Yeah, very good. Basically, the logarithm is e, so the base of the exponential should be e, and then you just swap on the sides of the terms.
So x equals to 1 over g.
Yeah, 1 over 3e. Absolutely. Easy. Okay, that's almost there. So we've got the x coordinate of the stationary point. That implies we also need the y coordinate if we're trying to find the stationary point. Probably not much to talk about there. right? Just shoving it directly into the original function. All the way in that x and that x, right? So as far as the y coordinate is concerned, y equals 1 on 3e natural log 3 over 3, so 1 over e, which is the same as e to the minus 1. And then you can do a bit of log related stuff, like for instance, because we have a power here, we can take that out the front, giving you negative 1 on 3e natural log e. When the base and bracket are the same, the logarithm ends up equaling 1. So we just leave it as negative 1 on 3e. I believe those should be our coordinate. 1 on 3e, comma, negative 1 on 3e. Sweet. Other than that, there's the applications of it, like finding the coefficients in the question. They only really did, oh no, they did another example of the big complex one. Do we want to practice any more of the simpler ones? Is there anywhere on this chapter section that's worth having a look at in more detail? Otherwise, we can do more content. This would be the next hardest bit, maybe, from a step in the same direction of the question 8.1. Do we want to practice any of this, or should I continue on with the content?
Can you do the question?
Say again.
Can you do the question?
Do the question 9?
Yep.
Yeah, sweet. So find the x-coordinates of the stationary points of this function where n is an integer greater than 1. So basically that's there to say if it was n equals 0, then, well, you know, nothing is really going on there. If it's n equals 1, that's just a quadratic, and you already know immediately where that stationary point is going to be. So it is again one of those questions with a generic power in there. Let's see how we go. The first step will be very, very similar. How do we start these questions off?
The derivative.
Yep, derivative. So when it comes to finding the derivative of this, what are we going to do?
We can separate the equations into two. So the inner equation is x squared minus 1, and the other one is the inner function to the power of n.
Yeah, that's right. So y of u to the power of n. So this, the path you're going down is the chain rule path. This is a composite function, and so we're going to treat it as such. Nice. We got our u, we got our y of u. What are we going to do with them?
Find the derivatives.
Yep, that's it. So u dash is going to be 2x, again, power down the front. Y dash of u, slightly trickier. What's that going to look like?
N times u to the power of n minus 1.
That's it. Again, power down the front reduced by 1, but now with the coefficients involved instead. Brilliant. All right, we got our derivatives of what we need. What are we going to do with them?
Yeah, we can put them into the chain rule thing.
Yep. So as far as chain rule goes, how do those get arranged?
The derivative of the inner function times the derivative of the outer function being applied in the inner function.
Yes, you're right. So these two things that we have here are going to be multiplied together. So 2nx bracket u, which was x squared minus 1, and that was to the power of n minus 1. Sweet. Okay. So we have our derivative. What are we going to do now that we have our derivative?
Set it to 0.
Set it to 0 is correct. That's it. Okay. We set our derivative to 0. How do we now solve for x, basically?
So there's 1x, so it shouldn't be too hard. So 2n to the other side, and n minus 1 to the other side as well.
So this is an x
oh wait,
in there as well, yeah? So
wait, is that, oh, wait, so that's an x.
yeah, that's the x from
Okay.
this. Yeah.
Okay,
If you want to refer to something, I can pull up on the screen share what we did last time for a similar question. You'll be looking in the step 2 section if you want to compare there.
null factor.
Yeah, null factor, that's it. 2nx is one of the functions multiplied by x squared minus 1 to the power of n minus 1. It's a product of two terms, null factor. 2nx equals 0 and x squared minus 1 power of n minus 1 is 0. At this point, there's probably not much to talk about. Dividing both sides by 2n, like you suggested before, gives you the x equals 0. This one might require a bit of revision. So how do we end up simplifying this one up?
Do we just set the x squared minus 1 to 0?
Yeah, basically, because it doesn't matter actually what this power is. It could be literally anything. There will be some root that would correspond to it. So you'd basically take the n minus 1 root of both sides, thus cancelling it out, leaving you with, yes, just the x squared minus 1 equals 0. And well, at this point, there's maybe only one gotcha, which is when you square root both sides, making sure we have that plus minus involved. That should be about it. I'm not seeing any domain. The other thing maybe that would be a gotcha would be if there's a domain associated with the original function. Like if this only allowed positive x, for instance, then the only possible solution here is now going to be x equals 1, of course. But there was this had a domain of all real, so we're totally fine with that. The only restriction was on n being greater than 1. That's about it. So that's as hard as this is going to get. So it's good we're able to smash through that more or less. So it's always going to be a null factor law approach and factorization if we need to factorize. It'll be a similar thing for question 10, probably using quotient rule to get your derivative there. And because you got division, you'll be doing some rearranging to multiplication. So probably, again, very similar. Do we want to practice that one or move on with content?
I say we move on with content.
Sure. Okay, so up until now, we've discussed how to find the stationary points. But as we discussed at the very beginning, as a quick reminder, there are multiple types of stationary points. You can have the maxima, you could have the minima, or you could have the stationary inflection points. We don't know what we've found up until this point. We just know that we found one of them. This next section is going to detail how you can actually figure out which one that you've found. By far, the most direct approach is going to be doing the double derivative and subbing in the x-coordinate that we've just found. So there's 3 little bullet points that'll tell you immediately which one you have. For anyone doing spec, technically, this isn't necessarily always true, this last bullet point here. It only is a sign that you potentially could have an inflection point, not necessarily guaranteed. For us in methods, that's not going to matter. It's always going to come out to be an inflection point.
To be sure, can we just like take the value a bit less than or more than the...
Yeah, exactly right. You can test either side. That'll be most effective on Tech Active, but then at that point you kind of just got the graph of it anyway, so you can just see it on the graphing tool. So yeah, if you want it to be absolutely sure, yeah, absolutely, just test both sides. In fact, what the textbook itself will do is get you to do exactly that, testing points either side of the stationary points that you just found, and then you get your overall shape of what you're looking at. I find this to be a bit unwieldy. It's definitely doable, but if you think about the amount of effort of working out that you're putting in to do this, let's say you've got these two stationary points that you've just found, you now need to sub in 3 separate values to figure out everything immediately left and right of those points. And then that gets
I think we've done this in last year at its 1-2.
Yeah, probably.
We were learning about qubits.
Oh yeah, so that was similar for cubics. You're absolutely right. Which was, what did they do exactly? I don't know. Did they test the points? Maybe they did. Yeah, they probably did. They probably tested again, and then if it was positive or negative, you'd be able to dot out the curve for it. I had the same sort of spiel last time, which is we don't really need to do that. We can just sort of know a few base rules, which is where does it start, where does it end, that sort of thing. This works. This is totally fine. If, when in doubt, like if you forget exactly what these bullet points are talking about, then by all means, just test points either side and get your overall gradients. But what I find is that this tends to be easier to do because finding the double derivative is just a matter of doing the derivative of the derivative, basically. So let's say we had this as our derivative. The double derivative would therefore be a linear. This is very quick and easy to do. Let's just power it in the front, reduce it by 1 again. Then, assuming you already have the x-coordinates or the stationary points, you just shove that into your double derivative function, and then whether it's positive, negative, or 0 will tell you immediately whether you found a max, min, or inflection point. That's the gist of it, really. So I'm using the same function that we had in the previous example one. We already now have those stationary points. Double derivative of this. So as a reminder, first derivative came from here. Second derivative, you're now finding the derivative of that function. Then from there, testing those values and then just comparing it to the criteria. So we test f dash dash of 2, that gets us a positive. The negative 2 gets us a negative. You don't even really care what the number is, so long as it's either positive, negative, or 0. So even quicker, if you are doing the arithmetic and you can clearly see you're going to have some positive or some negative, you don't really have to finish it to know ahead of time what it's going to be. But okay, so this one being positive means it meets criteria 2, so it's going to be the local minimum. This one being negative means it meets the criteria 1, so you've got the local maximum, which sure enough is going to correspond exactly to what we're seeing there. So it's a nice little thing. If you can practice this enough and just have it down, then works flawlessly. Of course, if this is like a criteria thing and you're just like, it's kind of, it's just another thing to memorize, then by all means, what you can do is you can test the points either side, and based on the slope, right, you're going to start with those stationary points. If you had a positive slope and then a negative slope, well, then you've obviously now got a maxima there. You can just look at the shape of the graph. Any questions so far on that? Cool. I'm not entirely sure what I was going on about here. Analyze derivative graph. Based on, so this is, I guess, an example of where you would have the graph of the actual derivative, and then by having that graph, determine the nature of an original f of x, which probably would have came from here at some point. Do we have one? Yeah, so it's these kinds of questions in the Cambridge textbook where you've got f dash and you want to use f dash information to then figure out, okay, yes, there's stationary points at these spots, but what's the nature of them as well? So let's see how we handle that. First things first, because this is an f dash derivative graph, all of the x-intercepts of them are going to be the location of those stationary points. All right. So we know off rip that whatever f of x was, the original function, it's going to have stationary points at -1, 2, and 3, because those are derivative equals 0 spots. From there, I'm taking it as from the double derivative approach here. So trying to get information of the double derivative, again, looking for the whole, where is it positive, where is it negative, where is it 0? It's the same way as if you're going from f of x to f dash. You're looking at the stationary points of the derivative. Those become the x-intercepts of the double derivative. Then from there, you split it up into your little sections and looking at the net gradient of each of those spots. So this is going to be a net positive gradient. It's going positive, 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 and then approaching 0. So we get that. So on and so forth. You can even look at the graph ahead of time and be like, okay, that's a positive cubic. I should therefore get a positive quadratic by the end of it. Then all we're doing is we're saying, okay, cool. I knew that these were the original stationary points. So now I'm just looking on my double derivative graph. Do I have a positive value there, or do I have a negative value there? This is just sort of fitting the theme, again, of using that double derivative approach. Now that I'm thinking about it in more detail, I think it's probably easier to not do that and more so just stick with here. That was fine and that works, and it follows the same sort of thing, so you don't have to memorize more than 1 or 2 approaches to a thing. But just having the derivative graph here, if you can picture things well enough, and if you're doing these questions enough times over, because this is a derivative graph, we have gradient information. So we know there's a stationary point here. Immediately left of it is negative gradient, and immediately right of it is positive gradient, because it's positive and negative y values. And y values on a derivative graph, they are gradient values. So in other words, if I start drawing up a little example, at -1, we have a stationary point somewhere. The left of it is negative gradient, because they're negative y values. So it's going to go down to the right. And then immediately after is positive gradient, because you're going into positive y values on the derivative. So if you're good at spotting that on the derivative graph, this is definitely faster. I just know that that takes a lot of practice to start seeing properly. Once you're able to do that, then you can obviously see how this will be a lot faster to do. Is there any questions about this shortcut here? Because I know that can take a bit of time to get used to. Sweet. As far as some CAS help, we have CAS functions like fmax and fmin. Those are probably a little bit more reliable than just doing derivative 0, because derivative 0, sometimes you have functions that have all sorts of craziness in them as far as like multiple coefficients in there. It's a little bit less reliable than just doing fmin or fmax, because fmin and fmax find not just stationary points, but also the true maximum or minimum of the actual function that you're trying to find the max or min of. So, for instance, if it wasn't a stationary point, it would find that as well. That's probably the main thing. Just making sure that you put domains on that gives you a bit more information, because you can then restrict your domain accordingly. Cool. Okay. Let's see. Let's do a bit of practice on the nature of stationary points. So what I'll do is I'll get a few screenshots going, because this one's probably a bit... This isn't in the textbook, by the way, this approach. This is just something that I know works. So because of that, I'll get a screen grab of this, put it in the chat for reference. That should be it, actually. Oh, okay. Let's see. We'll do a relatively easier graph just so we can get the stationary points quickly. Let's go 3A over here. That should be fine. We could actually sketch that if we wanted to, but either approach is fine. Y equals 4x cubed minus 3x power 4. Okay, so first things first is actually finding the stationary points. We've done a fair few practices of those already, so I'll just sort of run through this. 4 3s are 12, 4 3s are 12 again. Let it equal 0, x squared, 12 minus 12x. X equals plus minus 0, and x equals 1. Cool. I won't find the entire point. We'll just focus on getting the nature of the stationary points right. So these are going to be the x locations of our stationary points. How are we going to then go and find the nature of them?
Find the derivative of the second derivative?
Yep, that's it, second derivative. So y dash dash, we're now looking at this one. So that's going to be 24x and 36, oops, minus 6x squared. All right, what are we going to do with our y double dash?
Find the values and y equals to 0.
What are you saying, sub this equals 0?
Yeah.
It's a little bit different. So when we have our double derivative, what we're actually going to do is shove in these into it and then use that criteria. So I'll pull up on the screen share as well. Basically, we're shoving in the location of the stationary points.
Okay.
So in that case, we're going to have y double dash of 0, which, well, that's a 0 and that's a 0, so that's a 0. And then y double dash 1, which is going to turn out to be a negative number. Negative 12 in this case. Yeah, negative 12. Cool. So we now have our two answers there as far as what we can now compare. Looking at the criteria now, what's going to correspond to what? So which one of those x is the max, min, or inflection points?
Okay, so the first one is it could be a point of inflection.
Yep. And that's accurate language as well. Could be. A point of inflection is technically correct because, yes, sometimes in Spec they make it a bit harder and it doesn't necessarily always come out to be, but for methods this will always work. Nice. That's going to be the inflection point. The other one gives us negative 12, which therefore means what?
The local maximum.
Maximum, that's right. It's a number less than 0. So it's going to be the max. Now again, I did mention that we could kind of sketch this as well. One of the ways we sketch polynomials, of course, is via factorization. So what we would see is when we do our refactoring of this, taking the common factor x cubed out the front, 4 minus 3x, that should be an inflection point on the origin. All right, it's x cubed, it's an odd power. And sure enough, well, inflection point. So depending on how simple this polynomial is and your ability to sketch polynomials, it might genuinely just be easier to do this right? Like do a quick factorizing. That's going to cut at some, what's that going to cut at? Some positive value. It's going to have an inflection point here, net negative. You know, you can do all sorts of things to actually quickly sketch that and then just see what's going on there. This worked perfectly fine as well. It's more algebra focused than anything else. That is nature of stationary points. There is another example of like looking at the derivative graph instead. Let's okay, actually we do have a fair bit of time left because I was going to touch on also the max and min things that show up a lot in the exams, but I think we've got time to go through one of these as well. So this was the last thing we talked about, which was you have the graph of f dash. Now we want to find the nature of stationary points from that. So we'll just do 12a here. Based on the graph of f dash, what is the nature of the stationary points of f? I'll see if I can copy that down while you guys have a think. Okay. A couple of ways you could do it. I mentioned at least 2 ways that you could go about it. Finding nature of the stationary points. Maybe the first thing we would have to consider would be where are the stationary points actually? Like where are they firstly?
It's wherever the graph is touching the x-axis.
That's it, yeah. This is our derivative graph. So any spot where derivative y values are 0 is going to be the location of the stationary points on the original graph. Absolutely. So these are the values of interest here at -1, 1, and 5. How should we go from here? Figure out like what type of stationary point they are.
So at -1, it's the stationary point of inflection.
Okay, I'll label that inflection. We'll go through the reasoning behind them all afterwards. Were you going to do them one by one, or did you want me to?
Okay, I'll go through them. The other two are the other two are just local maximum and minimum. So at 1, it's a max. Yeah, it's a maximum.
Yep. Okay. Cool. So let's do a quick check then. So I'm assuming what you're doing there is looking at the gradients, or I guess more so like the y values either side of this to determine what you end up having. So a nice little way to do it is like a little freehand sketch of saying, okay, cool. So I got my point here. To the left of it is negative gradient, so it should be going down. And to the right of it, it should also be going down. So the only way that works is if, yes, you have an inflection point. Nice. Next one over here, again, point. to the left of it should be a negative gradient, so again going down, and to the right of it should be a positive gradient, so going up. So that one there looks like you got back the other way around, unless I'll do a quick double check. So left is negative gradient, right is positive gradient. Yeah, so these two are back to front then. Same thing over here. So left of it is a positive gradient. Positive gradient looks like this, up and to the right. And negative gradient on the right hand side. So these need to swap. So rather than trying to do them all in your head, probably these little quick pictures would be really nice for you to have if you're going to use that sort of approach. Is that all fair enough? The other approach, now this is a complicated function, so it'd be kind of hard to draw double dash, double derivative, because you'd be splitting it up into those sections and then going from there. If this is probably a preferred approach, once you can really picture it and draw these little mini solution sets there. Sweet. There's so much more in this chapter. We might need to revisit this again in like the review for like the Friday review, because there's so many more little things to touch on here. They're not necessarily all exam relevant though, so that's why we'll move on to what is more of the exam relevant stuff. So derivatives are fundamentally helpful for finding the maximum or minimum of a certain thing. Right, we've discussed that clearly and at length right now. As far as what that shows up in an exam, you'll be doing things like maximum area, maximum volume, lengths. These are the sorts of things that come up a fair bit. Tech-free or tech-active, very similar workflows. Tech-free, you're pretty much always 100% relying on doing derivative equals 0 and then going from there, because the maximum and minimum, or all minimum, is very likely to be a stationary point. In fact, it's basically guaranteed for tech-free. Tech-active, not necessarily the case. They like to do these little things where the max or min isn't necessarily a stationary point, which is where we start relying on our F-min or F-max to get us that instead. Let's have a look at an example. So they like to do these little trig-related stuff to try to trip things up. Actually, this one may or may not be... Yeah, it's kind of trig-related. So the goal here, find the value of x which maximizes the area of the trapezium. We've got a bunch of x's involved. We want to figure out which value is going to maximize the area. How big could it possibly be? We've done very similar questions in the past with polynomials. The first thing you want to do is create your expression for the function that you're trying to maximize. If we're trying to maximize area, we need an area function. This is a trapezium. If you don't remember your trapezium area formula, that's fine. You can technically break this up into two triangles and a rectangle, and then just add those together. But this will obviously be a lot nicer to go straight off and do. Yeah, getting all those together, our goal from here is trying to get the h, right? So this wasn't actually labeled, it was just a dotted line there. It is going to be the height of the triangle. So we just got to isolate that on one side. We've got a base, we've got a hypotenuse. This is Pythagoras at this point. A squared plus b squared equals c squared. And then just rearranging for the variable that you actually care about. We've now got our height, a and b, plug them all in, and then gets us our area formula. This one, yeah, question 18, it's a multi-choice. So this one was definitely a tech-active thing. So we're going to do our F-min or F-max, depending on what we're looking for. Should that say F-min? Yeah, okay, that's a typo. We should have F-max here in this case. Huh, what did I copy down? That was a bit stupid. It definitely says maximizes. Okay, so I just misread that entirely. Good thing I put that one in there as... Oh, no. So I literally just wrote F-min instead of F-max. It looks like that's still fine. Yeah, just pretend that says max. That will be the x value. The reason why this bit's in here is because it doesn't actually ask for the maximum area. It asks for the x value for which there is a maximum area. X value, of course, is going to get from our fmax. If you wanted the actual area, you want to now have to chuck that back into the area function itself. That's the workflow in a nutshell there. Any questions about that one? The other approach is if you do get tech-free for whatever reason, this wouldn't be too much hell to get through. Your area function is actually a little bit easier than what I left it as. I didn't even bother simplifying this because we were just going to cas it out anyway. But the x plus 3x is going to give the 4x. That's going to simplify all the way down to just a product law, basically. Well, a product law and a chain rule. You split it up into your two functions, derivative of each of those, do your cross product for the product law, and then let this equal 0. So this one here, again, you've got two terms separated by, in this case, a subtraction. These are polynomial-ish, and so we want to ideally try to get it into a spot where maybe we're using factorization, certainly at the very least getting rid of our divisions in there. The good news is the division here is the same as this factor, so when you do multiply both sides by that root, this ends up disappearing, or at least, it gets deleted effectively because you've multiplied by itself. The root part cancels. This quadratic in this case was just an x squared with a coefficient, so there's no factorization to be done, or needed rather, so we can just get everything over to the same side and or over opposite sides and divide all through. From there, a bit of root stuff, but yeah, that's just the gist of it really. That's all we needed. You would then maybe, if you needed to get the actual area, shove that back into the area function once again, which would look like that if you had to do it by hand. There's all sorts of ways this question can be answered, or asked rather. I think we've looked at this one before, maybe. They like to put these shapes inside of curves. Does anyone remember the key thing that comes up for these kinds of questions? I feel like we've done something like this before. There's a trick to these. That's all the way in step 1, which is when you're actually creating your area equation. Cool. I'm sure you can figure it out eventually. I was just curious if we recognize it immediately. One of the things you run into with when they're inscribed inside of a curve is, you create your area formula, which is half base height for the triangle. The base is cool, purely in terms of x. The height is now y. And you're like, okay, what am I going to do with y? We want to have only one variable left in the thing. Well, the y is shared by that curve. Since it is a point on the curve, y is the same as the function. And that's the spot that you really have to keep in mind. Because if you don't see that, then you won't be able to progress the question. But once you see it for the first time, you tend not to forget that that's the way you solve these. Other than that, this is solved the exact same way. Weirdly enough, this was a tech-free, right? This was 7A of maybe 2020-ish exam, something like that. And so, being able to do all of this stuff by hand is required. So they do really step up the amount of arithmetic you have to put into these questions. Now, one of the things that was challenging also about this one was that you get two solutions to derivative equals 0. So we'll ignore the math for now. We get these two solutions for derivative being 0. When there's more than one solution, you can do the double derivative test to figure out what's a max and what's a min. But with the applications, you usually get a little picture. And in this case, because we're trying to maximize the area, x just means where am I going to put this spot here? Or more specifically, like this line, right? Because x is the x-coordinate of this and also the x-coordinate of that, obviously. So these solutions here are therefore spots that you would now put that right-hand side wall. The question then becomes, would I rather put it here at x equals a half or here at x equals -1? If you put this b directly over a, you're not going to have a triangle anymore. That is, of course, going to be the minimum. So at that point, you can use a bit of logic to very quickly figure out that x equals a half is what would maximize the area. So putting it maybe there-ish. It's a unit circle, so well, kind of a unit circle, because that's -1, that'll be +1. A half would be around there or so. But it does not say find the x value for the maximum, it says find the maximum. So we then also now have to chuck that in here. 3 marks, by the way. So all this working out here, yeah, you can probably tighten this up a little bit. You may or may not need the quadratic formula. This could be done by a factorization technique. That might speed things up a little bit. But, you know, overall these are, yes, there's a lot of writing around here, but even the math is fairly extensive for 3 marks. Tech active, this would be way easier, of course, just Fmax and you're sorted. There's so many other examples, but I'll just be talking your ear off at this point. Maybe, yeah, we still got some time. Do you want to practice one of these, or should I just keep showing more unique examples?
Maybe one of these.
More of these? Yeah. Is that what you meant? Yeah. Yeah, sweet. Okay, so the reason I put this one in here as well is because now, yes, you're still finding an x, right? You're trying to still find the x for which there is a maximum, but this is where I think, because it was an angle, you had to start doing trig stuff. Let me just double check that. Yeah, we're using SOHCAHTOA related stuff here. So again, it's a trapezium. We had a very similar thing going on. We're trying to maximize area, so we need our area formula, area of trapezium, as before. H is usually the thing that is the tough part to get. Just by observation of the labeled terms that we have, we can very quickly get our A, the A being the base of the trapezium here. The B is a little bit more challenging. There's going to be a P portion from here to here, but we don't really know what's going on here and here. So the difference between this question and the last one that had a trapezium is that the last one had this as well already, I believe. We just have these. So, because we only have the hypotenuse of this triangle portion over here, we're going to start using our SOHCAHTOA to help us out a bit. So I'm just going to label that H. It is the height of the trapezium. And so SOHCAHTOA, we have our hypotenuse and we have our, this would be the opposite, right? So if the angle here is x, then opposite that is h, and this is the hypotenuse. So sine equals opposite over hypotenuse. I know I've got h for a not hypotenuse, but yeah, it's just opposite over hypotenuse here. Because we wanted to get h as part of the term, we're going to get h on its own. Therefore, we now have the height almost purely in terms of x. We do still have this p involved in there, though. Now, as far as finding b, we need to figure out this whole thing here. Now, this part, as I said before, is just p. It's just copied down from here. We just need to know what these parts are. Again, this is just a length of the triangle. This time it's going to be the cos portion, right? Because now you have the adjacent side of that x angle. So exact same idea to get cos. And therefore, because you've got one over here, the same thing as over here, these will be symmetrical. So we just double that up and then add the p to get the full, that full thing there. Chucking it all back in here. So we got our A, we got our B, we got our H in terms of P and X at this point. In this case, because p ends up being a coefficient of the whole thing after you do a bit of simplification, this was a CAS one, by the way, it's tech active, multi-choice. It didn't really drive any decision making too much. It's just a coefficient, and all coefficients do is expand like how big or how small the y values are. It doesn't necessarily drive where the x related stuff is. So it turns out to be the case that even though we do have another coefficient in there, when you do derivative 0 or when you do your f max over the relevant domain, so 0 to pi over 2, remember x is that angle there, right? So we're not going to have that go anywhere beyond a 90-degree angle. That'd be a bit strange. You do have to put that there though, because you are working with circular functions, and they will give you infinite solutions otherwise. There's so many more. I think there's this one, the tech active version of it, literals. Like there's a whole there's 5 full examples in there. So if you want to follow up more on those sort of things, this is in the max or min problems that'll be in the applications of derivatives section in the calculus module. So that'll be right there for you to revise. Any questions that need to be clarified about anything we looked at so far? And we can do more of this stuff in the review chapter as well, the review Friday. Otherwise, I'll let you guys enjoy the rest of your day.
Thank you.
No worries.
Thanks.
No
Have
worries.
a good day.
You too. Thanks.